Hi, my name is Cadet Heather Reed, and this is a video for Ma383. The problem statement reads, let a sub n from n equals 1 to infinity be a bounded sequence of real numbers. Define a new sequence of real numbers by y sub n equals sup of a sub k, where k is greater than or equal to n for each n within n. The first problem is develop the first 10 terms of the sequence y sub n from n equals 1 to infinity for the sequence a sub n equals sine of n from n equals 1 to n equals infinity. So here I have the series with the first 10 terms, and as you can see here, I graphed the series, and you can see there's an oscillating pattern between -1 and 1. If you graph it further than the first 10 terms, it'll be obvious to you that the sup converges to 1 because for each value it approaches between 1 and -1. So the sup will be 1 and the inf will be -1. So the second problem for this WPR is proving in general that y sub n equals 1 to infinity converges. So to go through the proofing guide, our first step is to put this problem into an if-then statement. If a sub n, where n equals 1 to infinity, is a bounded sequence of real numbers, and y sub n is the sup of a sub k, for k is greater than or equal to n for each n within big N, then in general, y sub n from n equals 1 to infinity converges. So our step 2 is our know. We know that a sub n from n equals 1 to infinity is a bounded sequence of real numbers, and y sub n is the sup of a sub k, where k is greater than or equal to n for each n which is greater than or equal to big N. Step 3 is our show. We know that we need to show that y sub n from n equals 1 to infinity converges. To start off expansion of our know, we have two cases. The first case is if a equals the sup of a sub n, then y sub 1 equals a sub 1, and y sub 2 is less than or equal to y sub 1. So to start off with this, we're going to let k equal 1. And if k equals 1, y sub 1 would be the sup of a sub 1, a sub 2, on through a sub n and beyond. If we let k equal 2, then y sub 2 would be the sup of a sub 2, a sub 3, through a sub n and beyond. So if a sub 1 is our sup for this sequence, then it is the biggest value in our sequence. With y sub 2, we removed y sub 1, meaning that we lost the biggest value in our sequence. So that means that y sub 2 is less than or equal to a sub 1, which is equal to y sub 1, because the sup of y sub 1 is a sub 1. And this new sup of this, y sub 2, would be a sub 2. For the second case, we know that if a sub 1 is not equal to the sup of a sub n, then the sup of a sub 1 through a sub n is equal to a sub 2, and y sub 1 equals y sub 2. We know this because if the sup a sub 2 through a sub n and beyond is equal to y sub 2, then y sub 1, where it starts with a sub 1, a sub 2, if a sub 1 is not our sup, and a sub 2 is the sup of this series, of this sequence, then y sub 1 would be equal to a sub 2. So then, if y sub 2 is the sup, where a sub 2 goes through a sub n and beyond, y sub 2 would be equal to a sub 2. Therefore, that means that y sub 1 will be equal to y sub 2. So, in general, we have the observation that y sub 1 is greater than or equal to y sub 2. And if we carry this through y sub 3, y sub 4, all the way out through y sub n, we would know that this trend would just continue. So that is one portion of the expansion of our know. So now moving on from what we just learned, we have epsilon is greater than 0, given the fact that y sub 1 is greater than or equal to y sub 2, which is greater than or equal to y sub 3. We set L equal to the inf of the sup, inf of y sub n. The inf of y sub n is the lower bound of our sequence, where L is the limit of y sub n. So L is the limit by, when we look at this graph, we can see that the removal of each successive sup from the sequence creates a new and smaller sup, So the sup, as you can see, is decreasing over time. We set this value to be our arbitrary value, the inf, so meaning the limit of y sub n is the inf, since the sequence is decreasing to that value. Because of this, we know that I is equal to the inf of x for every epsilon greater than 0. There exists an element that's x within y sub n, which is our sequence, such that I plus epsilon is less than x, where x equals y sub n, and y sub n is contained within our sequence y sub 1 through y sub n and beyond. So L plus epsilon is greater than y sub n, which is greater than or equal to y sub n for all n which are greater than or equal to m, since big N is equal to m and y sub 1 is greater than or equal to y sub 2, which is greater than or equal to y sub 3. So now that we've expanded our know, we're going to move on to the expansion of our show. The expansion of our show reads that we have to show L is the limit of y sub n and find big N so that y sub n minus L, the absolute value, is less than epsilon. And this is the epsilon definition for convergence. For all n which are greater than or equal to big N, where big N is equal to m. Okay. So now that we've expanded our know and our show, now we're going to move on to the clean proof. To start, let epsilon be greater than 0 and be an element of the reals, let that be given. By definition of inf of y sub n, y sub m is contained within y sub n so that L plus epsilon is less than y sub n. So now we're going to set big N equal to m. Because y sub n is decreasing, where y sub 1 is greater than or equal to y sub 2, which is greater than or equal to y sub 3, L plus epsilon is greater than y sub m and greater than y sub n for all n is greater than or equal to m, which is big N. So y sub n minus L is less than epsilon. By solving for epsilon, and negative epsilon is less than y sub n minus L. Because y sub n minus L is greater than 0, since L is the inf of y sub n. So, the absolute value of y sub n minus L is less than epsilon for n is greater than or equal to big N. So in general, the sequence y sub n, where n equals 1 to infinity, converges. And this completes the proof. Now moving on to part C. Develop a bounded sequence of real numbers a sub n from n equals 1 to infinity, where the sequence y sub n from n equals 1 to infinity does not converge to the sup of a sub n from n equals 1 to infinity. To start off with, y sub n equals the sup of a sub n, where k is greater than or equal to n. We're going to let a sub n equal 1 over n. For y sub 1, it would be the sup of 1 over n. So the sup of 1 is 1 over 1, 1/2, 1/3, 1/4, on through infinity. The sup of y sub 1 would be equal to 1 because 1 is the largest value within the sequence. Moving on to y sub 2, where k is 2, the sup would start at 1/2, 1/3, 1/4, 1/5, on through infinity. So the sup of y sub 2 would be 1/2, so y sub 2 equals 1/2. For y sub 3, you have the sup starting at k equals 3, so you have 1/3, 1/4, 1/5, 1/6, on through infinity. So y sub 3 equals 1/3. So because of this, we have the observation that y sub 1 is greater than or equal to y sub 2, which is greater than or equal to y sub 3. And if I kept going through successive iterations, you would find the same thing through infinity. So, based off of this, we see that the sup does not converge at any point. In fact, it decreases as you continue going through the sequence. So, y sub n from n equals 1 to infinity does not converge to the sup of a sub n from n equals 1 to infinity.
Special shout out to Rob Osborne for being my photographer. If you liked this video, like and subscribe for more.